Okay, so I'm gonna try to spend the first two lectures on diffusion flames, and although I have more than two lectures, there I have about three, but and I'll leave the last one to talk a little bit about turbulent flames. We mentioned earlier that there's one of the classification of combustion processes is in between premix and non-premix. So the classical non-premix flame is a candle flame, and I have put here some information about it. It showed the complexity of this very, very simple flame that sometimes, that once ignited, if conditions in the room where the flame is burning are calm enough without too wind and so on, you will obtain a very steady flame. The flame looks, as you see here, with this blue region, which is the main reaction zone. It's elongated clearly because of the entrained air and natural convection. You see the difference in temperature in the different region. The luminosity come from incandescent soot particle and other things that develop during the burning. But even the basic is quite complex, because once you bring in some source of energy or heat to light the candle, then what is formed is a little pool of liquid wax here. I try to draw it here schematically. Usually it's a little cusp, and then the wax is drawn along the wick by capillary forces, and it evaporates due to the heat, and oxygen diffuses in from the ambient. And even that simple situation is not very simple to describe mathematically. I made all kind of comments about the diffusion flame, some of which I already mentioned. The key thing is that the rate of burning is controlled by diffusion, and that's why we call it, in fact, diffusion flame. As I am showing here, natural convection is responsible for this elongated shape. If you are doing this experiment in low gravity, then you will get a very spherical flame, which is very blue, and just because diffusion is more or less radially. Okay. One would think that the simplest problem to examine will be a planar flame, in the same way as we have tried to describe a premix flame. So you would say, okay, you have fuel here and oxidizer here. You have a one-dimensional flow. The mass flux or mass flow rate is m, and there is a region here of where the combustion occurs. There is fuel here, no oxidizer. There is no fuel here, an oxidizer. Unfortunately, this problem in an unbounded domain does not have a solution. The reason is very simple. Since the mass flux is constant, then the equation for the fuel and oxidizer to solve are written here. You are already familiar with them. And if you look at condition very far away in the oxidizer region, the only solution will be a constant, because otherwise you will get a growing exponential, which is unacceptable. So if it is a constant, then it must be the value that you have supplied. And if that's the case, then how could it all be consumed at the flame? So I show it to you hand waving, but if you try mathematically to find a solution to this problem, it's not possible. So a steady, and I underlined here steady because, of course, if the fuel and oxidizer were separated by some diaphragm and you suddenly remove it, they mix and can burn, and you can have a diffusion flame, but it will be constantly changing or growing in time. It's not going to be a steady flame. So a steady planar diffusion flame cannot be sustained in a one-dimensional flow in an unbounded domain. The alternative is perhaps what we have referred to as a chamber diffusion flame, namely a situation where you assume the fuel may come from negative infinity. Sorry, I turned it around simply because this is a more natural way to draw the picture. So the fuel is coming here, a uniform mass flux, and the oxidizer penetrate at some boundary and then diffuse against the fuel, and a flame is established at some distance. But really, in order to create that situation, you need the oxidizer mass fraction to remain constant at this boundary, and that's hard to achieve because product will be diffusing out. And so basically what you need in order to establish this in the lab, to have a very fast stream that essentially wash the product and maintain more or less a uniform oxidizer at the boundary. I actually worked on this problem in my PhD thesis, despite the fact that some argue at the time that this is a no problem because you cannot really establish in the lab. So that's why I put here, can it be realized experimentally? In fact, I'm going to show you that it can. It took, of course, many years after my PhD that I worked with some people in Switzerland, and we were able to establish a non-strained, because this flame is through a uniform flow, so it's not under strain. It's a no-strain planar diffusion flame. And the reason that we wanted to study this planar form, because there were various flame instability that we wanted to understand. And when you have a simple configuration, both in the lab and in theory, you can do more because you can study multidimensional effect, time-dependent effect, stability effect, and so on. So I'm going to skip that for now and just mention the more classical problem, which is the Burke-Schumann flame. It's a diffusion flame established. I didn't draw the exact shape. We're going to talk about the problem specifically a little later. But essentially, Burke and Schumann in the 1920, 28 or so, created or studied that problem. You have a fuel coming from a cylindrical tube, and you have a concentric cylinder surrounding it where the oxidizer is coming, and there are walls here, and then you have a flame established at the mouth of the tube, which is going to be a diffusion flame because the fuel is coming from here and the oxidizer from a different origin. They provided the first mathematical description of such a problem in what they call the fast chemistry limit, which I will talk about in the next half hour or so. They, in fact, coined the term diffusion flame for these non-premix situation. In fact, they introduced a constant density approximation in that solution. In other words, they assumed that the mass flow rate remained constant, not affected by the combustion. Of course, they didn't use the word constant density, but effectively that's what they did. We are going to talk about that problem a little later. The other configuration that are commonly studied in the lab, yes?
These type of flames, they don't have a backflash?
That's a very good question, and I'm going to comment on that a little later. The common studies that have been discussed in the literature, apart from the planar unstrained flame that I listed here to contrast it with the counterflow flame, where the flame is under strain constantly, okay? So here the fuel and oxidizer come from two separate burners, and the two are well aligned, and then you have a planar flame that is established, and that planar flame is, as I said, under stretch all the time. Another configuration is the jet flame that you clearly see the description here. And the last case is spherical flame, which are nice and easy to discuss because of the spherical geometry. Typically, it's a droplet that evaporates, but droplets, unless it's in zero gravity, the flame will not be a pure sphere around it. It will have a teardrop shape because of natural convection, unless it's in a high flow, and then effectively the flame is nearly spherical. Alternatively, what people do, they inject the fuel in a thin tube, and you have a porous sphere, and then the fuel come out of the sphere in a more or less uniform way, so that to establish a spherical flame around it. So that's one of a configuration often used in the lab. The fuel can be either in a gaseous form or in a liquid form, so you can study various possible scenarios. The same thing is with the counterflow. There was a study in the poster that I have noticed where what they have here is a pool of fuel where it evaporates and it come out, so you can have that as well. So these are different configuration. Here is the spherical diffusion flame. This is what the droplet will look as a result of natural convection. If you can eliminate it somehow, for example, at low pressure, or in microgravity, you're going to obtain a more spherical flame. This is the counterflow flame, and that's the configuration and the planar flame that you establish. And this is the jet flame. Note that the jet flame can be attached to the mouth of the burner or to the rim, and sometimes it can be lifted. And if I have time, I will mention at least a few things about lifted flame and the nature of the combustion in this very close region, which is very important because that's what stabilizes the flame. Yes?
Is it pressure dependent that it lifts off? I mean, the velocity dependent, the lifting?
Yeah, of course. But it's not only velocity dependent, it can also depend on the concentration. Certain mixture, depending, in fact, on the Lewis number, some mixture will, as you increase the velocity, the flame get blown off. Some other mixture, when you increase the velocity, the flame get lifted more and more and more and more and be blown off only afterward. In fact, it can lift to extremely high distances, and it's quite nice to observe that. It's quite impressive. Okay, so so I will start the discussion with the planar unstrained flame, simply because it's a simpler mathematical problem to discuss. Here is the way it was established in the lab, and it was done at the EPFL in Switzerland. The oxidizer was introduced through approximately 800 to 900 needles that were put in at exact distance from each other, separated very exact distance between one and another, in order to provide, of course, uniformity. And so the fuel is the fuel is coming from the bottom, whether from needle or not, it's not important. But the oxidizer coming from these needles, and then the separation region allow the product to escape or to leave from that chamber, if you like. So you could see the picture, a blow up of this region here. Now, of course, you may ask, well, what happened when the flow is coming with the needle? Well, first of all, here is the planar flame. Just that's the proof. No need further. But you may ask, what happened near the needle? Well, you see the flow coming out of the needle, but there is a uniform flow coming from the bottom, which is stronger in magnitude, and so eventually turned back and leaves in the region in between, such that at a short distance of a diameter size of this needle, the concentration is almost uniform and the flow is uniform. And here is the measurement of the concentration. Of course, it varies when you are very close to the needle, and eventually it's almost flat. So there is a virtual boundary here that it's not exactly at the tip of the needles, but a little further away, which is the mathematical boundary where the oxidizer is supplied. Just a second. And this just complements this information. You see the stretch is extremely small. Of course, there are some effect at the boundaries, but it's minimal in the center, and the vertical velocity is much larger than the horizontal. The horizontal velocity is nearly zero. Yes? I can't hear.
How did he initiate the flame ignition?
Oh, you ignited with a torch, with whatever.
Isn't it confined?
Huh?
Isn't the flow confined?
No, it's not confined because remember, first of all, it's open at the bottom. In other words, you can stick in something here and ignite it. But I don't know, they probably have some electrode and do it in a more sophisticated way. There are no walls. There are some, actually there are. It's all glass, or at least something visible that you can see the flame through. But I think, if I remember correctly, there was a hole somewhere where they could stick something and just ignite it instantaneously. So it's not a problem. So here is the planar flame, the diffusion flame, and I want to emphasize again, it's different than the counterflow because there is no stretch. This flame, the flow is perfectly uniform through, and this was verified. And what you see here is to isolate the boundary effect. They inserted a little quartz cylinder, and so the center part was purely flat, and we could obtain cells and other things. We can find it pulsate and so on. Those are instabilities in diffusion flame that I did not discuss yesterday and probably won't have time to discuss. Okay, so mathematically we are faced with the following equation. The species equation for the fuel, species equation for the oxidizer, the energy equation. The reaction rate is typically of this form. We have assumed here reaction order 1 and 1 for the fuel and oxidizer, so overall reaction order 2. And the reaction rate is proportional to the mass fraction of the fuel and the oxidizer and the Arrhenius term. The boundary conditions are obvious. There is fuel here, no oxidizer on the top at this boundary, the green line. There is oxidizer and no fuel. And the mass flux through is constant. This is the M tilde. If you, an important thing is that in this diffusion flame problem, if you think from the mathematical point of view, what you call fuel and oxidizer is totally arbitrary. You can call oxidizer fuel and fuel oxidizer. Obviously, you don't want to do that, but the point is that there is a symmetry in the problem, and so I can also provide oxidizer here and get the fuel penetrating from the top, and you get an equivalent problem. So I'm going to discuss this configuration because that's what was sketched and presented here. So since we want to write the problem in dimensionless form, and we use the diffusion length, which is built from the thermal diffusivity divided by the incoming velocity as the length. Everything else is standard. We use the pressure, temperature, and density of the stream of the incoming stream as for units. And I have assumed for simplicity, although there is no need to do that, that the temperature of the fuel and oxide is the same. Obviously, one can change or have the temperature on one side hotter than the other, and So for simplicity, that was. So the only problems that are, the only parameters which are involved in the problem is the Dam-Kohler number, which is again the ratio of the flow time, right, divided by the chemical reaction time, the activation energy parameter, the stoichiometric ratio, and the heat release parameter Q. Okay. The first thing that we will do is we will assume unity Lewis number, and later we will see what happens if the Lewis number are not 1. So if the Lewis number are 1, we can use this coupling function. Remember that these combinations are conserved scalars. So these combination satisfy the equation equal to 0, nothing on the right-hand side, or nothing in the no reaction term. And being a simple linear equation, we can immediately solve them. So here is the solution of these three conserved scalar. There are some constant and another constant e to the x, and the constants are such that they satisfy all the boundary conditions that we have applied. Now, Burke and Schumann have introduced a really an ingenious idea. They said, well, we are going to assume that if the chemistry is very fast, then it will occur in some place where on one side there is fuel, on the other side there is no fuel, and on the other side clearly there is oxidizer but no fuel. So if you make that assumption, then immediately you see that that sheet or the reaction where the reaction occurs will be at the location where this combination must be equal to 0, right? Because at the reaction sheet there is neither fuel nor oxidizer. And from these two relations, I get immediately, in fact, from the top relation, I can also get the concentration of either the fuel in the region where the oxidizer is 0, because if this is 0, that's the solution for the fuel, and the solution for the oxidizer where the fuel is 0. And from the last two, you get the temperature. The first line will be the temperature where the fuel is 0, and the second line where the temperature, where the oxidizer is 0. So from the coupling function, we in fact find everything, and I will skip this, and we find the entire solution. So I described to you basically briefly what Burke and Schumann did. Later on, after some years, it's, I think approximately in the 1940s, it was recognized that the Burke-Schumann solution is in fact an asymptotic solution when the Dam-Kohler number d is very large. The Dam-Kohler number is the flow time divided by the reaction time, and if you take the limit that d goes to infinity, the reaction term implies that that should be in a it implies that that limit, the product YF, YO must go to 0 for the reaction to be finite somewhere. So this product equal to 0 is possible only in a diffusion flame. Clearly, it's not possible in a premix flame, because if it's 0, then you have nothing, right? But in a diffusion flame, it can be that on one side, for let's say x less than xf in the bottom part of my domain, there is only fuel. I may have, yeah, there is only fuel, but there is no oxidizer, so YO is 0. And on the top part, there is no fuel, so there is only oxidizer. And when you solve that coupling function, you set the 2 equal to 0, you get the location where the reaction occurs, or the reaction sheet. Note that the location depends on this parameter phi, which is the ratio of the fuel supplied on one side, the oxidizer supplied on the other, divided by the stoichiometric ratio. I don't like to call that equivalence ratio, because frankly there is no such thing as equivalence ratio in diffusion flame. The equivalence ratio changes constantly. There is an equivalence ratio at the region where they are mixed and they burn. But I would call it but nevertheless, it plays a role similar to the equivalence ratio, because it tells you if what you are providing is rich or lean, or in other words, it's with more fuel than, or more oxidizer than fuel. And so I will refer to it as the mixture strength. Okay, so again, from that solution, I told you that we can find the mass fraction, so you can write exact expression for them, and you can write exact expression for the temperature. And so this is the profile. The fuel coming from the left boundary is all consumed at the reaction sheet. The oxidizer diffusing from the boundary at x equal to 0, it's all consumed there. The temperature rises and drop and reach the maximum temperature here, which is the flame temperature, which is just the value of the temperature at that location. Since I know that location, I know the temperature, I can compute it. I use the term here adiabatic temperature because it turned out that, as you'll see in a minute, this is in fact the adiabatic flame temperature, but you have to be careful because in diffusion flame, it has a different, it's basically not in the same, it's not identical to the definition that I define adiabatic flame temperature, which was if you take a mixture of fuel and oxidizer, you burn it to completion, the temperature that you reach is the adiabatic temperature. So here, first of all, I wrote those in dimensional form, but here is why it is the adiabatic temperature, because it's the adiabatic temperature of a mixture which have this amount of fuel and this amount of oxidizer. And you can verify why. If you take the ratio of this to this, you obtain that it's exact stoichiometry, okay? This is the comment I want to make. But I want also to make another important comment, which I don't know how well this is known. The flame temperature is the adiabatic temperature in diffusion flame only when the Lewis number are 1. When the Lewis number is not 1, the flame temperature, and we shall see that soon, may go above or below adiabatic. You can have super or sub-adiabatic, depending on, because in a diffusion flame, the temperature depends on the means by which the fuel and oxidizer are brought together, unlike in a premixed flame. Okay. So this is that. I wanted to go back to this picture just to say that, note that the solution at the reaction sheet are continuous, but there is a discontinuity in slope, right? There's a discontinuity in the slopes. The slope, for example, of the blue curve here is finite, and then it's 0, and similarly in the oxidizer, and similarly in the temperature. Strictly speaking, this is not an acceptable solution unless you can show that the governing equation can indeed connect these two slopes smoothly. In other words, if the conservation law admits such a discontinuity. We are going to talk about that later. So let's move on. I'll skip that. Okay, so I want now to discuss a flame sheet approximation, but for non-unity Lewis number. From the previous experience, we see that all the three variables are continuous at the reaction sheet. So the jump in T, YF, YO is 0. You see that in the picture. And there is some discontinuity in slope, but we can immediately obtain a relation between the discontinuity of the in temperature in the fuel and in the oxidizer, and this is obtained simply by integrating this equation across the reaction sheet. In other words, you integrate it from xf minus to xf plus. And the relation is as written here, okay? In other words, it comes also from these coupling function when you keep the Lewis number in, but when you integrate once, this term doesn't contribute anything because of the continuity. Oh, anyway, so what we have here is 1, 2, 3 relation, 4, 5. There are only 2 relations here. 5, we have a 3 equation, second order, so we have a 6 order system. but we have 7 unknowns because we also don't know where the reaction sheet is. So we need 2 more conditions, but that was the idea of Burke and Schumann. YF is 0, YO is 0 on one side or another. That add 2 more conditions, and we can solve the problem for any configuration you like. The only question is solving the differential equation. Okay, so this is what the simplified problem will look like if you want to solve it for non-unity Lewis number. You solve this equation, the boundary condition, the jump relation, and you add the 2 complementary conditions that either YF or YO are identically 0. Note that I now call the flame position XS. The S stands for stoichiometry. In other words, this is known as the stoichiometric surface. And another thing to note is that the relation that you see here between YF and YO is interpreted simply that the fluxes of the fuel and oxidizer towards the reaction sheet must be in stoichiometric proportion. So this is the interpretation, and being in stoichiometric proportion, then the jump in temperature, what is the jump in temperature? Is the heat conducted on one side minus the heat conducted on the other side. So that's essentially all the heat which is leaving the reaction zone, and that should be related to those stoichiometric conditions. Okay, so this is the problem. Let's now re-examine it for the planar flame that we have discussed. So here are the solutions. The fact that there is a Lewis number in the equation, just add this Lewis number of fuel and oxygen in the exponent. And when you satisfy this jump relation, you obtain that the stoichiometric surface is given here. Note that when LE goes to 1, of course, this is exactly the same expression that I had before, but more importantly, the location depends on the diffusivity of the oxidizer, on the Lewis number. It will be located at different locations depending on the diffusivity of oxidizer. Why oxidizer? Well, it seems like the oxidizer is having a harder time to going through against the stream, and so that dictates how much reach the reaction zone, and therefore it depends on that. If I have inverted the situation and brought the fuel from the top, the sheet will depend on the Lewis number of the fuel. The next step is to solve for the temperature. Again, we know that the temperature is continuous, so I called it now Ts instead of Tf, which is the stoichiometric temperature, or the temperature at the stoichiometric surface. And this condition gives you the expression. Note that the stoichiometric temperature depends on the Lewis number. And so it's not the adiabatic flame temperature. And that's what's written here. So unlike premixed flame, where the flame temperature for all Lewis numbers is adiabatic flame temperature of diffusion flame depend on the Lewis numbers, or on the means by which the fuel and oxidizer are brought towards the reaction sheet. Only for unity Lewis number does it collapse or reduces to the adiabatic flame temperature. And you can see that if you replace this to 1 and you combine those terms, you get this. All right, so this can be generalized, in fact, to any surface. So if you have a reaction sheet, even if it's curved, then what you need is to write these jump relation across the normal rather than x. And I wrote here the relation in dimensional form. So what you see, I mean, if you divide by the thermal diffusivity, you will see the inverse Lewis number and so on, but it's exactly the same thing. The key idea is that the fuel and oxidizer are completely consumed at the sheet. The temperature and concentration are continuous at the sheet, and the fluxes are diffusive, and they are in stoichiometric proportion. Okay, here is the Burke and Schumann problem itself. The key simplification that Burke and Schumann have assumed, first of all, that the fuel is supplied in a cylindrical tube, and the oxidizer in another concentric duct. The flow is assumed to be parallel in the axial direction. In other words, V equal to U, and is not affected by the combustion, just moving up. The total mass flux in the axial direction is assumed constant. This is practically the constant density approximation. And of course, they used the idea that I presented already earlier, the infinitely fast chemistry. In other words, they will say that there is a sheet here. On one side there is fuel, on the other side no fuel, and only oxidizer. Okay, so they also assume the Lewis number are 1, although today we can do the problem with non-unity Lewis number as well, just following the jump relation that I described before. But for simplicity, I will keep it to be order 1. Now, in principle, what you are solving now is a two-dimensional problem. So conduction, diffusion would all appear as the Laplacian of some variable, right? Laplacian of y or t. Unfortunately, this is a complicated elliptic problem, and so it's quite difficult to solve. And so what Burke and Schumann did, they assumed that, or they neglected the axial diffusion. In other words, they say diffusion occurs only radially. Well, you can justify this if the flame is long enough compared to the radial distance. One can do it more mathematically, but I left here things in the spirit of Burke and Schumann. So if you neglect the d2 by dz2, what you have is the Laplacian is only that, and your equations are parabolic. And now because your equations are parabolic, you can assume that you have boundary condition at the mouth of those two concentric cylinders specified value, because a parabolic equation you can integrate forward. If it was elliptic, it's a problem, because that's exactly the question that was asked here. What happens if you have a flashback, right? In fact, if I were to solve the entire problem, let's say numerically, you cannot solve it from z equal to 0. You need to solve it from a sufficiently large negative z to allow the flame to even perhaps go below the mouth of the cylinder, because by diffusion, fuel can diffuse. If it diffuses fast, it can diffuse faster, and the flame can be established below, okay, which is like a flashback. So they avoided that by this idea. And so, what about gravity? I'm going to show you his solution, but what about gravity effect? Well, gravity effect have been neglected by Burke and Schumann, and they can be justified to be neglected when the Froude number is sufficiently large. In other words, when the effect of gravity relative to inertia is small. Otherwise, when the Froude number is small, such a flame would be affected by buoyancy, would be driven by buoyancy, and clearly the Burke and Schumann solution is not quite appropriate. Okay, but they have neglected essentially gravity. So the equation to solve are these, for the fuel and oxidizer are these. In fact, Burke and Schumann were mostly interested in the flame height, so they didn't go through computing the temperature. So they focused only on these two equations, and the boundary conditions are clear. The fuel is provided at the inner cylinder, the oxidizer at the outer cylinder. C is the ratio, or not the ratio, but the small relative. Yeah, it's made dimensionless, so C is the ratio of A to B, the inner to the outer radius. And along the duct, there is no flux, no penetration. Okay, so those are clear boundary conditions. So all you have to really solve is for this coupling function, YF minus YO divided by nu. Nu is the stoichiometric ratio oxidizer to fuel. This is an equation that can be solved by standard method, let's say separation of variables. So they solved it by separation of variables. The solution is of the form, because of the cylindrical symmetry, of course, Bessel function show up. And the solution is expressed as an infinite series of Bessel function. J naught is the Bessel function of order 0, which is this red curve. Bessel functions are something like generalization of cosine and sine, but that they decay, unlike sine and cos. And the J naught is 1 at 0, and then it decay as you go, oscillate and decay. And the coefficient A naught and AN are given here in terms of J1, which is the Bessel function of order 1. And those lambdas are the roots of J1. Those are the eigenvalues, which are all those dotted points here, right? So everything is known. You can evaluate as many terms in the series as you want, and talk about the flame height as well as the concentration of fuel in oxidizer, depending on which side you are. If you want the flame height, you set YF and YO as 0, and you get some function of space and of R and Z that describe the surface. And then the solution can be expressed in terms of this psi. So that's clear. So now I want to discuss a little bit what they found here. And here it is. So here is that function. And you can either has a situation where the flame converge towards the axis of the tube, or it converges towards the wall. And that turned out depend on the value of nu, or phi more accurately, the mixture strength. This is known as an overventilated flame, and the red is an underventilated flame. In other words, the blue one, there is enough oxidizer. In the red one, the red curve or the red surface would be obtained when the flame is trying to reach for the oxidizer because there isn't enough, let's say. But the blue one will be that there is enough oxidizer so it can converge to the center. And of course, you can obtain the height here. If you take that function and set R equal to 0, then you find the height. And in the other case, if you set R equal to 1, you get the height. So it's easy to find the height. And this was an example of the height for an underventilated case. If I have retained only one term in the sum, it's a rough approximation. You can retain few more and get better. But this is what it looks like. And if you do the overventilated case, you get a slightly different form, but you can evaluate it and plot these functions. Okay, the next problem is the counterflow problem, another problem which is commonly used in the literature. And, well, the mathematics is a little different, but the idea is the same. So I'm going to run it through a little faster. I just want to make one comment that in the literature, when the problem was discussed, it was first discussed under constant density because it's easier to do. Otherwise, it's more really a numerical problem. So if you assume a constant density, then what you assume is that the flow is known and is given by this stagnation point flow, minus 2 epsilon x and 2 epsilon y. Right? It's so that the velocity is moving from left to right, okay, here, and in the opposite way here. And a flame will be, a reaction sheet will be established somewhere in that domain, let's say at the location xs here, okay? If you don't assume a constant density, you can introduce a density-weighted axial coordinate, reduce the equation to something which look like incompressible. So there are simplifications that you could do, but eventually it's more complicated mathematically. Okay, so the problem is very similar in spirit to the one-dimensional problem that I did, with the only difference that there is the x here due to the strain rate. Now we have scaled the problem here using the strain rate in the scaling. Now the strain rate will give you a unit of 1/time, and so you can make out of the thermal diffusivity and epsilon. Epsilon is the strain rate. If you take the square root, you can make a unit of speed, and then the product d thermal times epsilon square root is a unit of length. So eventually the Damn-Kohler number that you obtain is the flow time, which is the strain rate, right? The reciprocal of the strain rate, divided by the chemical reaction time. So what control here the Damn-Kohler number is the strain rate. Okay, all the other parameters are similar to before, so I don't have to repeat what they are. And we are going to use the Burke-Schumann limit, so we're going to use the fact that either the fuel or the oxidizer is completely consumed at the reaction sheet. I'm sorry, that both are completely consumed, but one on one side, the other on the other side. Okay, so mathematically we need to solve the left-hand side of this equation, but this is not difficult. Those are error functions. So actually, before showing you the Burke-Schumann solution, I want to show you the limit d goes to 0. What is d go to 0? No reaction. So you have two streams coming one into another. They mix. So it's a pure mixing. That's all what it is. So you can solve these two equations. Clearly, the temperature, if we assume that it is the same on both ends, it's not going to change. It's going to remain T infinity. The mass fraction YF will drop, the YO will drop, and there will be a mixing of the two. Okay, so this is one limit. The other limit, of course, is of interest, is d going to infinity, a large Damn-Kohler number, which is a fast fast chemistry, right? The time for chemical reaction is very small, very short. Immediately as the molecules of fuel and molecules of oxidizer meet, they burn, right? Okay, this is the limit. So you can write the solution for the fuel, the oxidizer, and the temperature. Note that I have retained the Lewis number, and of course the fuel is 0 behind the reaction sheet, and the oxidizer is 0 ahead of the. So here is the solution. In fact, you don't see quite well here, but there are two curves. There is one which is the actual Burke-Schumann solution, the analytical solution, and the second one, it's a numerical solution where we have taken d sufficiently large. I think it was something like 100 after it has been scaled. And in fact, in this inset, you see the difference. So the dashed line is the Burke-Schumann solution, and the blue smooth line are the numerical solutions. So in fact, the solution is numerically can be computed to go smoothly through the reaction sheet and being totally consumed. Of course, to do this computation, you have to take extremely small steps in order to resolve that region properly, otherwise you missed it, right? Okay, so this is that, and we can write an expression, oh, and this is for the temperature, same as before. Okay, so now we can also write an expression for the location of the flame sheet or the stoichiometric surface. Unfortunately, it's an expression which is implicit. It's too involved. You cannot write xf equal to, but you can still plot it, and we are going to see in a minute the graph. And you can write an expression for the flame temperature, which is the stoichiometric temperature. And again, as before, it depends on the Lewis number. And if you assume that the Lewis number is 1, then the expression reduces to this simple relation. On the right, specifically, it's exactly the adiabatic flame temperature. Okay, so and on the left, for unity Lewis number, you see something very simple. The error function of the position is phi minus 1 over phi plus 1. The error function is a function that that asymptote, it goes like this. It's 0 at 0, and it goes to -1 here and to +1 here. So if you want, the axis is here. And so when phi equal to 1, which means that the mixture strength is exactly 1, it's like the stoichiometric ratio, then xf is exactly at 0, right? Because the error function of 0 is 0. If you provide the fuel and oxidizer at a rate which is the stoichiometric ratio, the flame will be exactly at the center, right? But otherwise, if phi is less than 1, in other words, if it's lean, then it's going to sit on the fuel side, and if it's rich, it's going to sit on the oxidizer side. And that's what this graph, in fact, shows. This is the location as a function of phi. Phi equal to 1 is here, and it's at 0. And if you bring in the Lewis number, you see that that has a significant effect, because the flame will be at the center for if the Lewis number is less than 1 at a leaner system will be at the center, so it will move to one side. And for the Lewis number larger than 1, it will be at the center only if it's sufficiently rich. Okay? So you see the effect of the location. The red curve is the one I've shown you previously, which is for Lewis number equal to 1. In other words, the flame is on the fuel side if it's lean, on the oxidizer side if it's rich. Otherwise, it depends on the extent of or the value of the Lewis number. What about the flame temperature? Well, here is a flame temperature as a function of this phi. And you see the adiabatic flame temperature is the red curve. So when the Lewis number is less than 1, you're going to get flames which have temperature super adiabatic, above the adiabatic. For Lewis number larger than 1, it's going to be below the adiabatic temperature. All right. So we have seen that two limits. We have seen the frozen limit, which is no combustion, pure mixing, and the temperature remain T0. I called it T infinity before T0, it's the same thing. And we have seen the Burke-Schumann limit, where the temperature is the stoichiometric temperature, Ts. But of course, it's interesting to know what happens as the Damn-Coulomb number varies. In other words, you don't always have an infinitely fast chemistry, and so you are interested to know what happened in between. When the two limits can be connected by a curve like this, which is perhaps a monotonic curve that connects one end to another, but it can also be connected by an S-type curve, which back up and then turn around. And of course, there have been a lot of interest at the time after Burke and Schumann to try to, people were not pleased or satisfied. It was a great idea and also very useful to obtain certain properties of the fusion flame, but one thing which it missed is extinction. It didn't describe extinction. And the first time that this was described successfully was by Fendel, who did the differentiate or solve the equation for intermediate values of the Damn-Coulomb number from the small to the large numerically. And he showed that the curve is typically the red curve, and the red curve clearly exhibit extinction. Because what happened if you follow the red curve, let's follow it from the Burke-Schumann limit, let's say. So here you have a complete combustion, okay? Both fuel and oxidizer are completely consumed. As D is reduced, the chemical reaction time is no longer very short, so it takes some time, and therefore the temperature will drop from from the stoichiometric temperature, and the fuel and oxidizer will not be necessarily completely consumed at the reaction sheet. There will be some left leaking through. And as you decrease the dam color number, temperature will further decrease, more and more leakage until a point, if you decrease it below that value, you drop to the frozen limit, which is extinction. So you follow this curve up to here, and then you drop to the frozen limit. This part is usually unstable and not physically realistic, and that's where the extinction value is obtained. If you follow the curve from the bottom, then you have a frozen situation. In other words, pure mixing, nothing happened. But eventually, at some point, chemical reactions start to be active. First, it's not significant because temperature is very low, but eventually there is enough mixing, there is a mixture, and there is also a slightly higher temperature, and then it ignites, it jumps to the Burke-Schumann solution. So this is, not necessarily to the Burke-Schumann solution, but to one of the upper solution, and then if you keep on increasing D, eventually it will be tending to that solution. So some of the interest will be to describe this curve in a more systematic way. This is where I put the arrow to describe. This is unstable, those are ignition and extinction. I think that's the end of this thing, and so it's pretty good timing, so we can stop here, and in the next lecture I'll talk about the structure of the diffusion flag.